Welcome. In this video I'm going to show you how you can determine various measures of qualitative variation using Python. I'm using Jupyter Lab and Python version 3.97. I have a separate video where I use my own library on this, so have a look at that one if you're interested. But in this one I will show you how it can be done without any other libraries. There are quite a lot of different measures. I'm not going to go over exactly which one you should be using or not. I'm just going to show you how you can actually determine the value of these. I try to group them a little bit myself. Some are based on the model frequency, some are based on the average frequency, some are based on something known as entropy, and you have so-called evenness measures. So to show you how to determine each of these, I'll need some example data. So I'm going to import pandas. So I can use the read CSV function from pandas to load a data file that I have available on my website. It's actually from the General Social Survey from 2012, but I adjusted it slightly just for these examples. I only need one field as an example, a nominal field with category, so I chosen marital status for this. And just to show you what that looks like, here are all the frequencies. Let me quickly just restart and clear all the output so we don't see every time everything. And of course I then need to reload these, but that goes pretty fast. Alright, for some of these we'll probably need the number of categories, which can easily be done with the len function, and the total sample size, which is done with the sum function. So we had 5 categories and there were 1,941 respondents, or at least people who answered this question. The model category, as you can see, is actually married. It's the one with the highest frequency. Alright, so there are a lot of measures, so let's dive into them. The first few are based on the mode, so I'll need that maximum frequency, which should give me that 972. The Freeman or variation ratio is simply the percentage of cells that are actually not in the model category. So we'll simply do 1 minus the frequency of the mode divided by the sample size. And that's all there was to it. The Berger-Parker index is slightly different. It doesn't do the 1 minus, and that's the only difference. So it's actually the percentage that is in the mode. A modified variation ratio is from Wilcox. He actually also uses the K, the number of categories, as you can see, and we have all of this. The big E one is actually just the sum, so summing over all of the frequencies, and you then do actually the mode minus the frequency, that frequency divided over that n times k minus 1. Or the alternative formula where you don't need to use a sum, and it gives the same result. Wilcox also had a one for a range variation ratio, so it's using the maximum frequency, the mode, minus the minimum and divided over the maximum. And again do a 1 minus in front of it, and we can simply use the min function to get the smallest one. Then there are quite a few on the mean base, so they actually average the frequencies, which should be the same as just the total frequency divided by the number of categories, which is 388.2. So Wilcox did this for average deviation, and this is actually mean absolute deviation, so it takes the difference of that average for each category and takes the absolute value and divides that by this 2 times average times k minus 1. And as you can see, the alternative formula has the exact same result. Gibbs-Boston used this quite for a few of his measures, or their measures, sorry. Almost the same, but as you might notice, there is no K, so this is not taking into account how many categories there are. With Boston M5, Gibbs-Boston M5, they do take that into account, and we have all of this, so it's just a matter of filling out this formula. For M6, slightly different, then they actually simply multiply that previous one, that M4 with K, and that then takes into account somewhat the number of categories. They also have one based on the variance for quantitative measures, where instead of taking the absolute value, you square these results. So we can simply square by doing 2 asterisks, and that gives us in this case 0.839. Now Alternatively, Gibbs Boston M2. This is actually the same measure. As you can see, it will give the same result. Or Smith-Wilson E1, also slightly different formula, but in the end it gives the same result. Now, often the standard deviation is more often reported. So similarly, we can simply take the square root out of the variance, or almost taking the square root out of the variance. And this looks scary, but there's no square root for in Python, so, or at least not by default. So we actually need to, and I see that I forgot to actually do that. We need to actually take the square root by taking this to the power of a half, and that should give you the right result. All right. Then there are entropy-based ones. They are often done with the proportion, so we divide all of the frequencies by the sample size, and we often will need logarithms. So NumPy actually has a nice one, log and log2, so we can import those. And let's get started with the most famous one is the Shannon-Weaver entropy, or sometimes just called Shannon entropy. It's the summation of the proportions multiplied by the natural logarithm of the proportion, and natural logarithm in Python is simply log. There we go. Then we have Renyi entropy using log base 2, and it's actually raising the proportions to a particular power. So let's do that, and we then get 2.09. Wilcox H. Rel also uses this. Again, the proportions times that log 2 of the proportions, sum those and divide them by the log of k. This will actually give the same result as Pilou J, who's using the Shannon-Weaver entropy, and divide that by the natural logarithm of k. Alright, and then we have the Sheldon index, again using the Shannon-Weaver entropy, but then doing an Euler raise to that, divided over the number of categories. We can get the Euler value by using the exp function from math, which comes with Python. The hype index is the last one of these entropy ones, again using the Shannon one, again raising e to the power of that minus 1, and then divided over k minus 1. So very similar like the previous one, but just in the numerator and denominator you subtract 1. Then we have diversity and evenness measures. This is going to be a long video. There's the Hill one, which if you set an alpha, if that's 1, you simply raise e to the power of the Shannon-Weaver one entropy, and otherwise you raise it to the power of alpha, the proportions, and you sum all of those, and then you raise that to 1 over 1 minus that alpha. So here simply the NA. If it's 1, actually that should be, of course, if HSW is the, yeah, so we should do actually EXP HSW. But I didn't set alpha to 1, so actually this can be ignored for now. But otherwise it should do the sum, and then pi to the power of alpha, and then sum of that, and then raise to the power 1 over 1 minus alpha. For the evenness, Hill actually uses the 2 of them, so you set an alpha and a beta, and then you do the exact same as above. So again, I need to adjust this one, and then you simply divide those two by each other. So then we have Bula, who actually have an evenness and a diversity measure. The evenness looks big, but most of this, the k we already have, the n we already have. This O is actually the minimum. You take for each category, you take the proportion, or 1 over k, whichever is smaller, and you sum all of those. So we can do that in one go with Python by doing here minimum of x, or 1 over k, for every x in our proportions. And then we can simply fill out the formula, and we get our Bula E. Now the diversity is simply this one multiplied with the number of categories. Simpson D is the same as Gibbs Boston M1. It doesn't actually use any entropies or something. It's just the frequencies times the frequencies minus 1 over n times n minus 1. So fairly straightforward with the sum function, and in this case it turns out to be 0.33 roughly. There's also a population version of this where you can simply sum the squared proportions. So that gives you a slightly different result. And sometimes instead of doing it as a diversity, they see it more as a dominant score, and then you do 1 minus each of these. So that gives a slightly different result. It's actually just the opposite then. Then D4 is actually then the same as Gibbs and Poston M1, so we can actually see that as these two now being the same. Gibbs Poston M3, however, is slightly different, taking these squared proportions, subtract the minimum, and here we also have everything we need, the K and the P minus, so we can simply run the function, or actually the formula, immediately. The same goes for Smith-Wilson. It's using the natural logarithm of that d2 and the natural logarithm of k. Divide those two over each other and you're done. And for Smith-Wilson, it's that d2 value, again 1 over d2 times k, and we're done. Two more to go that I couldn't really fit into another category. There's Wilcox mean difference. It actually goes over all possible combinations of frequencies for each category, subtracts the two from each other, takes the absolute value and sums all of that. So what I'm doing here is I'm going over a range from 0 to k minus 1, so all categories except the last one, and then for j go actually into the next category until the last one, and every time determine the difference between the two frequencies. Sum all of that up by doing a continuous addition of this, and then in the end divided by the number of categories, the sample size times the number of categories minus 1, and subtract all of that from 1. Finally, case B, which is this scary looking formula, but it's not too bad. This weird looking pi is actually the product, so it's similar like the sum, the weird looking e, but instead of doing a plus you then do a multiplication every time. If you import from the math library the prod function, it will do that for you. We're multiplying each frequency with k and divide that by the total sample size. Then we sum, once we have that product, we actually raise it to the power of 1 over k, which is the same as taking the kth root out of something. Then we square those results. As you can see, we need that square over here. We have a 1 minus, and then there's a big square root again. So we raise it to the power of a half, and then a 1 minus in front of that again. Alright, and that is how you can roughly determine about 25 different measures of quantitative variation with Python. These are all the resources I used. I hope this video was helpful, and thank you for watching.